x squared. And as I told you, yesterday, I'll not prove, the second one because it is similar to the first one. That's why I'll not prove it. And as I told you, when you guys want to prove this one, so you follow the exact same step as we did yesterday in order to get the derivative of cosine inverse. And just keep in mind, the reason why we have -1 on the top is just, when you differentiate cosine, you guys will get minus sign. Don't forget it. Otherwise, you will get the same steps. And I am recommending you, to do your best to calculate the derivative or to prove it by using exactly what we did for sine inverse. Today I'm gonna do now the third case. Okay, so the third case is the derivative of tan inverse, and I'll prove it. Keep in mind these three derivative formulas. For derivative of sine inverse, you guys can see 1 over square root of 1 minus square. And for cosine inverse, you have -1. That's the difference between the first formula. But for tan inverse, the derivative is equal to 1 over 1 plus x you squared. Okay, so keep in mind this formula. Okay, and later, next we'll see here how to prove it. I'm gonna just get out from this slide and go to my notes, and we'll see. Okay, second. Oops, where's my? All right, give a second to get. All right. So as I said, we did number 1. Now we're gonna do 3, and it's gonna be similar to what we did, for secant for sine inverse. We want to prove that tan inverse has its derivative equal to 1 over 1 plus x squared. And to do so, you guys start by setting y equal to tan inverse of x. And you apply, tan in both sides of this equation. So the left-hand side becomes tan of y when you apply tan on both sides. And on the right-hand side, you guys will get tan inverse of x. So the tan and the tan inverse cancel out, and the right-hand side becomes only x. So you'll get the tan of y equal to x. And using implicit differentiation, we'll differentiate with respect to x. We'll differentiate this equation that I highlight here with respect to x. So when you differentiate with respect to x, you guys will get exactly this. This step going to be derivative of tan y with respect to x equal to dx by dx. And when you differentiate tan with respect to x, so since the tan depends on y, we need first to differentiate it with respect to y, and after we'll differentiate y with respect to x. And this is exactly what the implicit differentiation says. When you differentiate tan of y with respect to y times dy by dx, the right-hand side becomes dx by dx, which is equal to 1. Now I'm going to differentiate, sine tan of y with respect to y. And based on what you guys did in Math 1500, so the derivative of tan of y is secant square of y. That's exactly what we got here. So this is the derivative of tan of y with respect to y. And times dy by dx, this is equal to 1. And when we isolate, dy by dx, so we have to send secant of y to the denominator on the right-hand side. So you guys will get dy by dx equal to 1 over secant square of y. Okay? Now I'm going to express, my secant in terms of tan in order to be able to express, the whole function in terms of x. And you guys know from what you did in high school, secant square is equal to 1 plus tan squared. I'm going to remind you the formula. Here's exactly what we got. So secant squared here is exactly equal to 1 plus tan squared. Okay, I just replace or express my secant squared in terms of tan. The reason is I know exactly what is tan of y. That's why I'm going to get the denominator in terms of tan instead of in terms of secant. Okay, and as you know, tan squared of y means tan y to the power 2. And now we're ready to substitute, y by its value. So from this second last step, when you guys substitute this y by its value, y equal to tan inverse of x, you guys can see here, I'm going to substitute here y by its value. At the beginning, y is equal to tan inverse of x, you substitute by its value. And the right hand side now becomes 1 over 1 plus. So this bracket, as you can see, is exactly equal to x, is just the result that I highlight here. Your tan of y is equal to x. So that's why the denominator here becomes only 1 plus x squared, and you're done. Is there any question? So you all good?
Sir, how
Yeah.
do you express tan in how did you turn sec square into tan square?
As I said, this is a formula that you guys supposed to see in high school. I'm just gonna, so later on I'm gonna give you a couple of formulas that you guys have to memorize. It's gonna help you to transform. This is some trigonometric functions. Okay, just give me a second. I'm gonna just write it here to remind you all these formulas that you're supposed to know. So I'll not prove it because we don't have time to do it, but I'm gonna just remind you all these formulas. Okay, so what I use in this case, one of the formulas that you guys know is cosine square of x, okay, plus sine square of x. So everybody remember this formula? Yeah, exactly. Okay, so it's equal to 1. And so we have a couple of trigonometric formulas that you guys supposed to know in calculus too, because later on when it comes time to integrate functions involving trig functions, most of the time you guys have very complicated functions that you need to simplify, and to do so you need these transformation formulas in order to simplify your integral. So I'm going to give it to you. I'm going to give you some of them. So for example, the other formula that I can give you is secant, your mic please. So secant square of x is equal to 1 plus tan square. And to answer to your question, this is exactly the formula that I use to prove, the theorem is equal to tan square of x. Okay, so this is the formula that I use. And we also have another formula saying cosecant square of x, I'm gonna write it here, is equal to, you guys remember?
1 plus cot square x.
1 plus
Cot square x.
Pardon?
Sir, cosec square plus sec square is equal to 1.
Yeah. It's going to be
cot square x.
It's a plus cot square x. Okay. And we also have cosine square of x minus sine square of x. Okay, so this is equal to, remember, this is equal to cosine of 2x. It's not a square here. It is a cosine of 2x. Okay, and so we also have cosine. So you guys have to take, you know, these formulas and keep them in mind. We're gonna use them later. So cosine square x also can be written as was plus cosine of 2x. Okay, we don't have square here. Cosine 2x over 2. And one more question. One more formula. We're gonna, yeah, so 2 more. So sine square of x is also equal to
2 sin x cos x.
1 minus cosine 2x over 2. And one more. So when you guys have sine of 2x,
2 sin x cos x.
sine 2x can be written as 2 times
Cos x.
sine x cos x, exactly. Sine x times, okay, cosine x. Okay, so in the proof that I showed you a couple of minutes ago, I use, you know, the second formula here, secant square of y equal to 1 plus tan square of y. Is it okay? And as I said, you guys have to keep in mind all these 7 formulas. And when needed, I'll give you more formulas. Is it okay? And as I said, we already proved number 3. And to do it, we use, you know, this formula. Any question? You good? All right. Now let's see the fourth one, the fourth formula. When we want to differentiate the function cot inverse. I'm going to remove all this. So number 4, you guys can see here, the derivative of cot inverse is similar to the derivative of tan inverse, very close to tan inverse. The difference is just the numerator where you guys have a negative sign. And the negative sign is just obtained from the derivative of cot, because when you differentiate cot, you guys know it's going to be minus secant cosecant square. So that's why I have minus here. I'll not prove number 4 because the proof of number 4 is similar to the proof of number 3. So if you guys want to prove number 4, you follow exactly the step that we use in number 3. And you know, the third formula. Okay, that I gave you a couple of minutes ago in order to get it. So since you know 4 is similar to 3, that's why I just proved number 3 and leave 4. You guys can try it at home, and you can also try number 2 by following exactly what we did for number 1. These two functions are almost the same. So that's why if you follow exactly what we did for 1, you guys will be able to get number 2. And when you do what we did for 4, what we did for 3, if you did it for 4, if you do it for 4, sorry, you will be able to get the solution. Second last formula, this one I'm gonna prove it because it's totally different to the other functions. So we differentiate the secant inverse with respect to x, and the formula says this is equal to 1 over x root of x squared minus 1. Keep in mind this formula too, and we will prove it next. 1 over x times square root of x squared minus 1. Okay, so I'm gonna let you give you 30 seconds to write down the formula, and we will prove it. Is it okay? All right. Number 5. So would like to get here the derivative of secant inverse. Again, we're gonna use the same technique by setting here y equal to secant inverse of x. Okay. And when we apply secant on both sides of this equation, the left-hand side becomes a secant of y, and the right-hand side becomes only x because the secant and secant inverse cancel out, as you know. And using implicit differentiation, I'm going to differentiate, the highlighted, equality here. So you differentiate on both sides of this equation with respect to x. And you guys get the left-hand side derivative of secant y with respect to x is equal to the derivative of x with respect to itself. And so when it comes time to differentiate secant of y with respect to x, we need first to get its derivative with respect to y and multiply it by the derivative of y with respect to x, as you know, the implicit differentiation says. And the right-hand side now becomes 1 because you have, dx by dx. And as you know, the derivative of secant y from 1500, you guys know derivative of secant y is equal to the secant of y times tan of y. So this product is just obtained from the derivative of secant of y. And we just copy the last part here, which is equal to dy by dx, and the right-hand side is still equal to 1. Now, isolating your dy by dx, it means you have to take this product and send it to the other side, the right-hand side. If you do so, you have to divide, since you have a product. You divide by secant y times tan of y. And you guys will get here from this step, dy by dx is equal to 1 over secant of y times tan of y. Okay? So now, since I know the connection between secant of y and x, so it means I can substitute this one by x. Now the question is how to express my tan in terms of x. And to do so, I need to transform my tan and express it in terms of y first. And I'm going to use the exact same formula that I showed you before, and we used it in the previous proof. So we've seen, tan squared is equal to secant squared minus 1. That's why if you take tan of y, you have to take the square root of secant squared minus 1, because what you guys have under the square root is only tan squared. Allow your mic, please.
Freaking liars.
Your mic, please. You guys turn off your mic.
For where to go in the first place.
You can't tell me about this.
Sams Fardin.
This never happened, do you understand?
Of course.
Sams Fardin, your mic, please.
You think it could not happen?
So when you guys get into the class, you have to switch off your mic. avoid, you know, the background noise.
I don't know who you're talking about. Sam, are you with Sam?
Hello, your mic, please.
Why? What's wrong?
You can mute it. You don't have to, you know, switch it on.
Sorry, he muted his mic. So
All right. So we have secant of y times tan of y dy over dx. And as I told you, secant of y, its derivative is secant y tan of y. So that's why we'll get, you know, 1 over secant y tan y. And based on the formula that we've seen a couple of minutes ago, tan of y, tan square, we know, is equal to secant square minus 1. So that's why tan of y is going to be square root of secant square minus 1. So now, just keep in mind secant square of y is exactly equal to secant of y, you square it. That's the meaning of this notation. So now we're ready to substitute y by its value. When you guys replace your y by its value, so at the beginning you see y is equal to secant inverse. I'm going to replace this y by secant inverse, and I'll get exactly the left-hand side of the result here. And secant to y here from the second last step, I'm going to replace secant y by its value. You guys can see secant y is what I exactly highlight here. Secant of y is equal to x under the square root. Again, you have secant of y, you square it, going to be just x squared minus 1. And this is, you know, the derivative of secant inverse of x. Any question? Is there any question?
Nope.
Right, thank you.
Just for a second, I'm just writing.
Oh, okay, sorry.
Just 30 seconds.
Okay, give me a second. I'm gonna. All right. So let me know whenever you're done.
Done. Yep.
Thank you. All right, so we're done with 5. So I'll not prove, you know, number 6 because you guys can see it's similar to number 5. Okay, so here the negative sign is obtained from the derivative of cosecant, because you guys know derivative of cosecant is equal to minus cosecant times cot. That's why we'll get a negative sign. So basically, if you guys want to prove number 2, I'm recommending you to follow exactly what we did for number 1, because the two functions are very close. If you want to prove number 4, you follow exactly what we did for number 3, because the two functions also are almost the same. And if you want to prove number 6, you follow exactly what we did for number 5, and you're good. And one more thing, you guys have to memorize all these 6 formulas. So next, I'm going to give you some examples. Okay, and here, so we have to use the chain rule to differentiate, you know, this first example. The reason is the first example here is a composite of two functions. We have the cos inverse as a function, and we also have x squared minus 3 as a second function, which is the inner one. And when you guys differentiate this function, you have to apply exactly this formula because we have cos inverse. You apply this formula. The difference here is instead of x, we have a function which is equal to x squared minus 3. So it means you use this formula by replacing this x by x squared minus 3 in our example. So it means when you apply it, so it's going to be here x squared minus 3, and here it's going to be x squared minus 3, you square it. And you have to differentiate the inner function. I'm going to give you quickly here how to do it when you guys have to use the chain rule. You want to differentiate, for example, cosine inverse of g of x. In my example, g of x is equal to x squared minus 3. This is what I want to get. So I'm going to apply the formula. Just I'm going to remind you the formula. In the same page, you guys can see exactly the application. Keep in mind, we've seen in the previous slide, cosine inverse of x. So it's a derivative based on what we did in this previous slide. This is just the formula number 2. This is equal to minus 1 over, this is minus 1 over square root of 1 minus x squared. Okay, I'm just reminding you this formula. I'm talking about this one, the derivative of cosine. That's exactly what I copy in the next slide. So back to the slide you guys see is exactly the same thing. But now we have to apply this formula. But in this case, just keep in mind we have g of x. We don't have x. So that's why the formula becomes here when you differentiate it is going to be equal to negative 1 over square root of 1 minus is going to be gx because we have gx. Yeah, for our example, yeah, it's going to be x squared. So I'm just going to give you the general formula. Okay, so you guys see it's just this formula, but instead of x here we have gx. It is exactly the same formula. Since we're using chain rule, we have also to differentiate this inner function, and the derivative we multiply here by the derivative of g, which is equal to g dash. Okay, and this is the formula that we guys have to use to differentiate this function, where the gx is equal to x squared minus 3, and as your friend said, it's going to be here x squared minus 3. You square it, and here is going to be the derivative of x squared minus 3. Is it okay? So that's why you need to memorize this formula, okay? Otherwise, you'll not be able to get the derivative of this function. So you need to memorize this one, and that's exactly what we apply to get this part. And we multiply now by the derivative of the inner function. Any question? All right. So let's move on now to see how to solve our question here. Right. Here is our question. So we want to differentiate now this function. And as I said, this is going to be my gx. And as I told you, it's going to be negative 1 over square root of 1 minus gx. You square it times g dash. And we repeat the same factor here. You don't need to simplify, you can leave it like that. Times, now when you differentiate this bracket, you guys will get 2x, and this is your final answer. Is it okay? Any question? So it means anytime you guys have a to apply the chain rule when you want to differentiate, you know, a composite of two functions involving cosine. So you use the formula that we've seen previously. Cosine inverse of gx going to be -1 over square root of 1 minus gx squared times g dash. All right. So let's see now the second example. If you guys are done. For second example, we have a product of two functions, x squared times sine inverse of 3x. Product of two functions to differentiate, as you know, you guys have to use the product rule. Okay? And I guess you guys remember the product rule.
No, sir. May you explain again?
What's the answer?
Not the answer, I said the product rule.
Use the product rule.
Yes, I remember.
Okay, the product rule says when you want to differentiate u times v, for example, okay? In our example, u is equal to x squared and v equal to sine inverse of 3x. And the product rule says calculating the derivative of this product is equal to calculating the derivative of the first factor times v plus
u times derivative of v.
Derivative of, and this is, you know, the formula that we have to use. In our example, this is u, and all this is v, and we have the product here. Is it okay? So we're going to use this product rule. Right? Ready?
Yep.
All right, so let's see the product rule now. So you're gonna apply it here. As I said, you have u times v. So you need first to differentiate u, this part here. All right, when you differentiate x squared, it becomes 2x. This is your u dash times v plus u times v dash. So when you differentiate, you know, x squared, it becomes 2x times the sine inverse, plus now x squared times the derivative of sine inverse. And to differentiate sine inverse at 3x, you apply this formula number 1 when x is replaced by 3x. And you will get 1 over square root of 1 minus 3x squared. You guys can, you already have, you know, the formula number 1. Just take this formula number 1 and you substitute your x by 3x, and you will get this second factor here. Times now, as I told you, the derivative now of the inner function is exactly what the chain rule says. And at the end, so we have just to calculate the last part here. So I'm just going to copy here the first term, going to be 2x times the sine inverse of 3x, just exact the same thing. So these two factors, we keep them. We don't need to change anything. So the denominator here, 3x squared, just is 9x squared, times the derivative of 3x, which is equal to 3. Any question? You all good?
Yes, sir.
All right, so let's see now the third example. So third example, f of x is equal to tan inverse at x cubed, the whole thing to the power 7. Okay, so we have a function to the power number. And you guys have also in 1500 how to differentiate such function. Okay, I'm just gonna remind you the chain rule in this case. So if you guys remember, if you want to differentiate g of x, for example, to the power n, you want to differentiate this, because this is exactly the case. In this case, g of x is equal to tan inverse of x cubed, and n is equal to 7. And do you guys remember in this case the chain rule? We differentiate it. It's gonna be
n g of x raised to n minus 1.
N times or plus?
G of x
G of x
raised to n minus 1.
Okay, to the power n minus 1.
And the differentiation of g of x.
Exactly. Times here the derivative of g of x. So we have to use this formula in this case. Okay, you guys can see exactly in this case g of x is equal to this function, the whole thing here, and n is equal to 7. So it means it's going to be 7 times tan inverse to the power 7 minus 1 times the derivative of tan inverse at x cubed. Okay, we're going to apply this formula for number 3. And you guys have all this in this formula in 1500. Okay. All right, so now let's see how to use it. So as you can see, you guys have tan inverse of x cubed to the power n when n equal to 7. And based on the formula that we've seen, is equal to n times g of x to the power n minus 1, which is equal to 6, 7 minus 1, times the derivative of tan inverse at x cubed. So next step, we have to calculate the second bracket here, the derivative. And based on the tan inverse, the derivative of tan inverse at x, guys, remember, or you look at, formula number 4, you guys can see the derivative of tan is equal to 1 over 1 plus x squared. But here it cannot be x squared because we have x cubed here. That's why instead of x squared, we substitute the x by x cubed. It becomes x cubed squared. Times now, because of chain rule, derivative of x cubed, this function, the inner function here. And to conclude, so the second factor here becomes 1 over 1 x to the power 6, because we multiply these two exponents, it becomes x to the power 6. And the derivative of x cubed going to be just 3x squared. And we're done. Is there any question? Okay, I'll let you write down the answer. And if you guys have questions, let me know. You all good, guys? Regarding
Yes.
question number 3. All right. All right, so let's see the next example. Maybe our last example. So now we have f of x equal to cosecant inverse of 1 over x. Okay, so we know the derivative of cosecant inverse. I'm gonna write it down here. Again, you guys can see it. So we've already seen, the formula number 6 that that's the number 6 that we have to use in this case. And number 6 says the derivative of cosecant inverse of x. I'm gonna write number 6 again. So the derivative of this function is exactly equal to -1 over x times square root of x, you square it, -1. So we have to use this formula. And for this function, since we don't have x, we substitute this x in our formula by 1 over x. So it's going to be here -1 on the top, but the bottom becomes 1 over x here instead of x. And the square root here, under the square root, you guys will get 1 over x squared minus 1. And don't forget now to multiply with the derivative 1 over x, because we have the composite of two functions. And in this case, you have to use, the chain rule. Okay, so back to the solution. You guys can see here, applying what I said. So f of x equal to cosecant inverse of 1 over x. You apply the formula as I told you. It's going to be -1. And you substitute x by 1 over x because of this inner function. This x you substitute by 1 over x times the derivative of 1 over x. And here we copy the same thing. And so 1 over x squared becomes just 1 over x squared. And when you calculate the derivative of 1 over x, it becomes -1 over x squared. And you're done. Is there any question?
No, sir.
All right, so this example, concludes the second chapter. And in our next class, we'll start, the third one. And keep in mind, you guys will get your first lab this Friday. Okay? And maybe 2 days before the first quiz, I'm gonna post, some past quizzes. Quiz 1. Okay? So keep in mind, you guys will get quiz 1 and we'll get on I guess 21st, and you will get just like 2 days to submit your quiz. The exact date are already available in the course outline. So if there is no question, I'm just gonna give you here some practice question, give you a few minutes to solve them. All right, so here is a past quiz 1 coming from last winter. Yeah. Not last winter, yeah, so it's gonna be winter 2019. All right, so you guys have to calculate the limit of sine inverse of pi x, okay, over root of x, when x is approaching to 0 from the right. And when you guys substitute x by 0, the numerator becomes sine inverse of 0, which is equal to 0. The denominator gonna be 0, it means you have undeterminate form. Okay, I'm gonna give you like 5 minutes to solve this question. Okay, keep in mind you have 0 over 0 undeterminate form, and when you guys have undeterminate form, 0 over 0, so we've seen from chapter 1, it means we can use the L'Hopital's rule. So it means this question, in fact, combine the first chapter and the second one, because we want to use L'Hopital rule, and to do so, we have to differentiate here the inverse function. It combines, the 2 chapters. Okay, I'm going to give you 5 minutes to solve it. And after that, we can see the solution. Okay, go ahead. All right, so mom, this is not marking. Okay, it's just for practicing. This is a past quiz 1. Okay, so we finished early this chapter, so I just wanna let you practice some question in order to know exactly what gonna look like, the question in your first quiz. All right.
Yes,
and as
sir.
I mentioned, and as I mentioned before, a couple of days before the first quiz, I'm gonna post, some past quizzes, and you guys can use them to practice.
Sir, is the answer 0?
Pardon?
Answer is 0, sir.
No.
Sir, is the answer infinity?
Pardon?
Is the answer infinity?
No, that's not. It's a number.
Okay.
So to differentiate the numerator, you guys need to use the first formula as we did for one of the examples. So you need to know the derivative of the derivative of root of x. All right, so 1 more minute.
Sir, pi.
No, very close, but it's not pi.
Is it root pi?
Pardon?
Root pi? Root
Yep.
over pi? Yeah.
You got it. All right, so let's see the solution. So is anybody get root pi? Only one or two people got root pi. All right, thank you. So let's see the solution. It's right here. And this question is out of 4. So as I mentioned before, I told you, you guys get here 0 over 0 undeterminate form. So you have to mention it. It's 1 mark, as I told you, because this indeterminate form gives you the right to use L'Hospital rule. You cannot start by saying, I'm going to use L'Hospital rule without telling me the reason. So that's why if you don't write this, you guys will not get the 1 mark here. So now when you use L'Hospital's rules, you need to differentiate the numerator and the denominator. So the derivative of the denominator is quite easy. You guys can see it's going to be just 1 over 2 root x. This is the derivative of root x here. For the numerator, so you guys need to apply, the derivative of sine, formula number 1. When you apply, it's going to be 1 over square root of 1 minus the square of this, all this, the square of root of pi. So that's why now, if you square root of pi x, it becomes only pi x times the derivative of root of pi x. And derivative of root of pi x is equal to 1 over 2 root pi x times the derivative of pi x. So derivative of pi x equal to pi. That's why the numerator is equal to pi. And now you guys can see here, you can simplify some terms. So here you simplify 1 over 2, and here 1 over 2. You simplify this 2, and 2 is the denominator here. You simplify root x here, and here root x. But if you simplify root x from this bracket, it remains root pi only, because root pi x is same as root pi times root x. So when you simplify the root x, now since you simplify 2 root x, the denominator becomes only 1, because 2 root x is gone now. And here 2 root x is gone. And you guys will get, since the 2 root x is gone, it remains inside the bracket, just pi over root pi. That's exactly what we got here. And this part is also gone. That's why I don't have it anymore. And now letting x approaching to 0 from the right. So the second term here under the square root becomes 0. And then you guys will get 1 over root 1. It's going to be 1 times, and this bracket is the constant. That's exactly what we got here. It's pi over root pi. And pi over root pi, you can leave it like that, or you can simplify it by rationalizing the denominator. And to do so, you multiply up and down by root pi. When you multiply here, root pi is going to be pi root pi. And here you multiply by root pi, going to be root pi square equal to pi. So the pi cancel out, it becomes a root pi only. Correct?
Yes.
Is there any question?
Sir, can you explain the last part again?
Second last line here?
Yes.
Or here, the last part?
The last 2 lines.
Okay, so what they said here, from here, you calculate the limit when x is approaching to 0. It means you replace this x by 0. When you replace by 0, it's going to be just 1 over root 1 is equal to 1.
Oh, yeah.
Okay,
Yeah,
and it
yeah.
only remains this part because this part is already 0. So it remains only the bracket, and that's exactly what I have here. And this part is also equal to this by rationalizing the denominator.
Okay, thank you.
Well, all good?
Sir, in the first part, we are using the sine function, right?
Sine inverse.
Yeah, sine inverse, right?
Yeah. And if you look at, sine inverse is, the formula number 1 in the PowerPoint slide. So when you differentiate this, if you remember, sine inverse of x, that they're going to be 1 over square root of 1 minus x squared. So here you don't have the square because it was a square root. If you square the square root, it becomes only pi x. And now you have to differentiate this part here to get pi over 2 root pi x. All good? All right. Can we go to the next question? Okay, guys?
Yes.
All right. I'm going to skip the B part here and ask you to do this one. Okay, so you guys can calculate this tan of secant inverse of pi over 4. You calculate this value. This is not derivative. This is, what we did, in the previous classes. And we've seen, easiest way to calculate this is by using the triangle, if you guys remember. I guess we used it yesterday too. Okay, I'm gonna give you 5 minutes to do this one too.
Sir, root of 105 by 4.
Pardon?
Same.
Root of 105 by 4.
By 4.
Oh, I don't know. I didn't see the solution, so we'll see. Okay, I'm gonna give you a few minutes.
Got the same answer.
Okay.
So you got the same answer?
Yes, sir.
Yes.
There is 105 by 4.
Pardon?
Is it 105 by 4?
Oh, I don't know. So we'll see. I don't remember the solution. Okay, so we'll see it in about 1 minute. All right, so let's see the solution. Is it what you got?
Yes, sir.
All right, so we did this kind of example many times. You start by setting theta equal to secant inverse of 11/4, and it means secant of theta is equal to 11/4 by applying secant on both sides of this equation. And now you have to create your triangle here, and when you do it, secant we know is equal to hypotenuse over the adjacent side. So it means the numerator should be my hypotenuse. That's what I did here. And the denominator should be my adjacent side equal to 4. And the remaining part gonna be the opposite side. I call it L. I wrote here D, but it's supposed to be L. So in this case, by using Pythagorean theorems, so L gonna be 11 squared. So 11 squared gonna be 121 minus 4 squared gonna be 16. And you guys will get root of 105. So it means tan of secant inverse is going to be tan of theta. And tan of theta is equal to opposite side, which is equal to L over the adjacent side, which is equal to 4. And L we know is called root 105. And we're done. Any question?
No.
No, sir. No, sir.
All right. If there is no question, I'll let you go. And that's all for today. And next class, I'm gonna introduce, the third chapter. Okay. And before letting you go, I'm gonna take the attendance, please. All right. Are you done taking this the solution?
Yes, sir.
Okay, because I'm gonna stop sharing my screen. Is it okay for you guys to
Yes.
stop sharing my screen?
Sure.
Okay, thank you. Okay, I'm gonna take the attendance.